Okay, so now we're going to carry on with concept number 6. And you all might be wondering, why am I wearing a different outfit? It's because I'm filming this full lecture over a course of a couple of days, right? And just for today's filming, my iPad is now battery, so we are back to the old style of teaching on the whiteboard. But nevertheless, if you head down to the link in the description, if you click on the link, you'll be able to get your hands on the worksheet where it has all my handwritten workings, including for whatever we're going to be going through in this video for. So if you want to get access to that, just check out the link in the description. Otherwise, we'll carry on with the next concept, which is the formula for the series of an AP. Okay, so just to add on to whatever you already know, right? An AP is essentially a type of sequence, right, where there is a constant difference. So we can say that it's a sequence with a constant difference. So when I say it's a sequence with a constant difference, we can look at something like this, right, where let's say I have 2, 5, 8, 11, and so on and so forth, right? And you can see that the common difference over here is 3. So I have plus 3, plus 3, plus 3. Now, remembering the formula for series, right? What does series actually represent? A series is essentially the sum of the terms, right? Sum of the terms in a sequence. So how do I then formulate a formula to derive the series of any AP, given that we know that an AP has a very standard structure where each term is a constant difference of the previous one, right? We know that the general formula is Tn equals to T1 plus n minus 1d. Now, at this stage, right, if you have already learned this topic before, you might have been memorizing your way through this whole entire chapter. But the thing is that you don't really need to memorize it simply because there's a way to understand it. And my aim here with this lecture is to help you build some intuition behind the formula. Okay, so now if we take a look at the example AP, right, then let's say we want to find the series of this AP. Let's say 2, 5, 8, 11, 14, 17. This series has a total of 6 terms, right? This is T1, T2, T3, T4, T5, T6. Now, if I want to find S6, S6 is basically the sum of the first 6 terms, right? T1, T2, all the way until T6. If we look at the AP, the interesting thing about this is that the first term and the last term, if we add up the values over here, right? If we take 2 plus 17, we actually end up with 19. If we take 5 plus 14, we actually end up with 19. And if we take the 2 middle terms, you end up with 19, right? So using this unique property of an AP, we can derive this very interesting observation. So with this interesting observation, what can we infer about the series of an AP? For a general AP, if we start from the first 2 terms, the first term and the last term of an AP, and then we sum them up together, and then we move on to the next 2 terms, and then we move on to the next 2 terms, every single pair will add up to the same value. So with this very interesting observation, how do we then formulate a very general equation, right? But before we formulate a very general equation, let's try to formulate or come up with a structure for the formula for this series of an AP over here, right? For this S6 over here, I can say that I have 6 terms, and therefore I have how many pairs, right? If I have 6 terms, I divide by 2, I will get 3 pairs, right? 3 pairs. Now, what's the value of each pair then? Then, very simply, if we take the first term plus the last term, we get the value of each pair, value of a pair. And what this does is that it ends up with 3 times 19, right? Which gives you 57. And therefore, we are able to derive the sum of all of these terms without having to manually add them up. So to generalize this in terms of n, let's say I want to figure out what is my Sn then, right? So this is S6. Now, for the sum of the first n terms of an AP, if I have n terms, I will have n over 2 pairs, right? And what's the value of each pair? It's simply just the first term plus the last term, Tn, right? Because if I have n terms, the last term will be the nth term. And remember earlier on we said that the nth term over here can be written in the form of T1 plus n minus 1d. So what this means is that I can put this inside this formula here to further expand it and end up with n over 2 times 2T1 plus n minus 1d. And this is the formula for the series of an AP. Right, so you can see that even though technically, yes, you could memorize this, but understanding how it works makes things a lot more interesting, right? Because now you are able to see how the relationship between each term is like in an AP. Right, so this is the formula for the series of an AP. So, with that said, take this down because we have come to the end of concept 6. And now what we're going to do is that we're going to move on and try to apply the concept right now. So, if you want to try to tackle this question, you can actually download this question from the link in the description as well. Just click on the link to download the worksheet. And you're able to see the question on your own device, right? Otherwise, you also can try to take a look at my screen over here. So I'm going to give you some time to actually tackle this question. And when you're ready, you can come back and unpause the video. If not, right now, we are actually going to go through this concept over here. So I hope you have taken this down because I'm going to erase this. And let's now try to do this question to apply the formula that we have learned. Okay, so let's try to tackle this question over here. We want to find an AP whose first term is 2 and the nth term is 32. And when we say the nth term is 32, that means the last term of this AP is 32. So let's first define, right? So let Tn, let's define the general term first. So let Tn be the nth term of this AP. So Tn equals to T1 plus n minus 1 of D, right? This is the formula that you have learned. So T1 is 2 and the T last, right? The last term is 32. And we know that the sum of the first n terms, Sn, which is n over 2 times T1 plus the last term TL, will give me 357. So what you realize is that right now we are just trying to find the value of n, right? So when we want to find the value of n over here, we can sub in this and this values into it, right? And you end up with n over 2 times the first value plus the last value gives you 357. Simplifying this, you get 34 equals to 357. n over 2, or rather in this case n, will be 357 divided by 34 times 2, and you end up with 21. So that is how we derive the value of n in this context. Now, given that the kth term has a value exceeding 100, so when we say the kth term exceeds 100, we are talking about the individual term. So in this case, since we know n is 21 over here, we can find out what is the common difference first, right? So T21 is 32, right? We know that the last term is the 21st term, which links back to this. So 32 can be written as 2 plus 21 minus 1d. From here, we get that 30 is 20d. And therefore, the common difference of d is 1.5. Hence, the general term of this whole entire AP, right, is given to be Tn equals to 2 plus n minus 1 of 1.5. So we want to find out what is the k term where Tk is actually bigger than 100. So we actually need to form an inequality over here, right? And then when we form this inequality over here, okay, you just end up with your k over 2, sorry, not k over 2. We're using back this formula over here. 2 plus k minus 1 of 1.5 is bigger than 100, right? Solving for this, we get that k minus 1.5 is bigger than 98, right? And when you solve for this, right, k is actually bigger than 98 divided by 1.5 plus 1, you get that the smallest k value, right, the least k value that you get is actually 67, right? So I'll just leave this to you to key this into your calculator. And what you end up with is that k minimum is 67. And that's the final answer to this question over here, right? So this is the full step-by-step solution. If you've got any questions, feel free to leave it in the comment section of this video as well. If not, we pretty much come to the end of this concept over here. And we're going to be moving on to the next concept. And the next concept is actually proof that something is an AP, right? So how do we prove that something is an AP, right? Because in the world of sequences, there are so many sequences. So the way that we prove that something is an AP is to leverage its unique characteristic. What is an AP? And that is having a constant difference. So to prove that something is an AP, that a sequence is an AP, we simply just take Tn minus 1 equals to a constant, right? We just need to show this, Now, the reason why we show it this way is because if I take two successive terms, right, the general term, two successive general terms, and I minus them away from each other, and if I get a constant that is independent of n, then what that means is that this definitely has to be an AP, right? And usually when I teach this concept to my students, I get a couple of questions whenever it comes to this type of proving. The first question being is, and you might want to ask yourself this as we are going through this concept. The first question that I get is, can I use a specific term, right? So can I use T2 minus T1 equals to a constant to prove, right? So this question actually stems from a place of wondering whether we can, instead of using the general term of n and n minus 1, and use a specific case of T2 minus T1 instead. Right? I want you to think about this question right now, because the answer to this is actually no. And it's not because this is wrong. If it is indeed an AP and you take T2 minus T1, you'll definitely get a constant. Right? So it's not saying that you won't get a constant. But using this way to prove that this is an AP is insufficient, right? And I'll explain this to you using an analogy, right? So let's say you want to prove that something is an AP, right? If, let's say, I got a sequence like this, 2, 5, let's say here I have 8, for instance, 8n, okay, maybe 2, 5, then 8n, then, for instance, 16n squared, for example, something like this. Right? This is a very random sequence. Now, if I nitpick the first two terms, right, and I take 5 minus 2, of course I'll get 3, right? But then if I take this, I get a difference with a variable in it. So, whenever we want to prove anything in math, right, it's always, if you want to prove that something is true, you have to prove it for all of its general cases, right? So this is what we call the universality, right? You want to prove that for all values of x, it obeys a certain law. But if you want to disprove something, you only need one specific case, right? And that is, you just need to prove that one specific existence defies the whole theorem and the whole theorem will break. But if you want to prove that the theorem is true, you have to prove that generally for everything it complies, right? And that is why in math it's so much easier to prove that something doesn't work rather than prove that something works. Because in order to prove that something works, you need to prove that it works for every single thing, which is the general case, right? But to prove that something doesn't work, you just need to nitpick one specific case, because if one specific case fails, that means the theorem does not hold true for everything, right? So that is why the answer to this is no. If you want to prove that something is an AP, you need to prove the general term is a constant, right? So this is the idea behind it. And just a second tip, right? Usually questions, they won't give you Tn directly, because if they give you Tn directly, then it's going to be very, very simple, right? And then there's nothing much to test you on, right? You can just simply take Tn minus 1 and get a constant. So usually what questions will do is that they'll give you Sn. Okay, so I'm just going to write this over here. Usually questions, they'll give Sn. And from Sn, you are supposed to derive Tn. But how do we derive Tn from Sn? Right, the idea is very simple. Sn is the sum of the first n terms. So T1 plus T2 plus all the way until plus Tn. Now, if I want to get rid of all of this, right, if I want to get rid of all of this, end up with just Tn. I will need to subtract away T1 plus T2 all the way until Tn minus 1, right, to get Tn. And what you realize is that T1 plus T2 all the way until Tn minus 1 is just Sn minus 1, right? Because we are talking about the sum of the first n minus 1 term. So a very helpful formula that you can use in this case is that in order to derive Tn, Sn is basically just, Sn minus Sn minus 1 will give me Tn. So usually these two formulas that I've highlighted over here, they are usually used in a pair. And when we use them in a pair like this, it allows us to derive Tn and therefore derive the constant. Okay, and with that said, we have come to the end of this formula over here. We're going to be trying out this question over here. Feel free to pause this video to attempt this question, and I'll be writing the solution to this question on the board over here that we'll go through together. Okay, so let's start, and we want to show that this logarithmic equation is an AP. Now one look, of course it doesn't look like AP, right? It's a logarithm. How can it be an AP? But actually it's an AP, and I'm going to show you why. So even though this is an AP, you might be thinking, right, if this is an AP, how come the general term look like this? The truth is that most of the times, APs don't look like APs, right? And that's the beauty of this whole chapter, is that something might look like something else, but at the core of it is an AP or a GP, like we'll discuss later on. Okay, but we're just going to take it as it is, given that Tn is log 2x n minus 1, where x is a positive real constant. Show that this is an AP for all real positive integers of n. So how do we show this? We need to show that Tn minus 1 is a constant, right? So first thing we're going to do is that we're going to derive Tn minus 1. And the way we do this is we're going to substitute all the n with n minus 1. So we end up with n minus 1, which is log 2x n minus 2. So if we take Tn minus Tn minus 1, you end up with log 2x n minus 1 minus log 2x n minus 2. Now, you might be thinking, how do I then generalize this, right? How do I reduce this to the point that I only get a constant? Now, the truth is that it's actually just your laws of logarithms. I'm going to show you why. First thing you can realize is that you can bring this forward. If you recall your laws of logarithms, you can bring forward the power to be a coefficient. So you end up with just n minus 1 of log 2x. And then here you end up with n minus 2 of log 2x. So you realize that you can factor out the log 2x over here. And then what's left is just n minus 1 minus n minus 2. Reducing this, right, you get n minus 1 minus n plus 2. Then the n will strike out, right? So you're just left with just 1. So you're just left with log 2x 1, which is just log 2x. Right, and remember from the start, defined as a positive real integer, which means that log 2x is just an integer. Or it's not an integer, but it's just a real constant. Right, so since x is a positive integer, log 2x will just be a real number that's independent of n. Right, so to conclude, since Tn minus Tn minus 1 is a constant independent of n, right, then this means that this is an AP, proven. And that's it for this over here, right? So, very interesting question, and it really forces you to accept the fact that not every single thing needs to look like an AP in order to act like an AP. And this is one very classic example of that. Okay, so take this down, and we're going to move on to the next concept after this. Okay, so I'm assuming that you've already taken this down. We'll move on to the next concept right now. Okay, real-world application of AP. Now, there's not much value for me to add over here because this portion is just more so for me to tell you that usually APs are tested in the context of real-world questions, especially in the higher stake exams like your prelims or your promos or even the A-levels itself. So that is exactly why for real-world question, you need to understand these formulas intuitively. Because if you don't understand them intuitively and you don't understand why they are done in this way, then when it comes to real-world questions, you won't be able to identify the scenario, and you won't be able to identify what formulas you need to use. Because most of the time in real-world questions, it's a feeling, right? You have to feel what formula you need to use. It's a gut feeling. And you can only get this gut feeling when you actually understand what you're learning in the first place. So I hope that I've been doing a good job so far in explaining all these concepts to you. Okay, so if not, we will try out this question over here to understand this real-world question over here. Okay, so I'm going to erase this on the board, and we're going to try our hands on this question over here. Okay, so looking at this question over here, we have a NATO logistics commander was tasked to deliver goods to someone, and the commander delivered 1,000 tons of goods on the 1st June, then 1,100 on the next day, and so on and so forth. Right, so each day's delivery was 100 tons more than the day before. After several days, then he had to change the plan so that the subsequent days was 100 tons less. And by 15 June, he had delivered a total of 21300 tons of goods for the past 5 days. On which day did he deliver the most goods to the camp, right? And how many tons of goods did he deliver on this particular day? Okay, so first thing is that we realize for the first line over here, where each day is 100 more and then the next day is 100 less, right? This is a classic structure of an AP. So we know that, okay, I know that there's an AP concept over here. And to understand this real world concept, we want to try to map this out, right? We want to try to sort of draw this out. Okay, so let's try to draw this out over here. On the first day, 1st June, I deliver 1,000 tons of goods. On 2nd June, I deliver 1,100 tons of goods, right? And this carries on until the so-called nth day, right? End of June. But to make it a little bit more general, a little bit more abstract, I won't use June, I use the days, right? Because we know that there's this day 1, day 2, then all the way until day 15, right? So instead of writing it this way, I'm going to write it in a clearer way, okay? So this is the day number, and this is the mass delivered. So day 1, day 2, all the way day n, right? Day 1, I deliver 1,000. Day 2, I deliver 1,100. And then until day n, right? On the nth day, how many goods will I have delivered before I had to change my plans? So you see that this is an AP, right? You have you plus 100. So by the end day, I will have delivered 1,000 plus n minus 1 of 100, right? Because the constant difference over here is 100. And then after that, if this is the day, that the last day of this plan, right? And then on the n plus 1 day, so on the n plus 1 day, over here, I change my plans. So you can think of it as this over here has its own AP, and then over here, it has its own AP as well, right? For the n plus 1 day, my first value, so to speak, is 1000 plus n minus 1 or 100. Then I minus 100, right? This minus 100 is because it's the start of the new plan, right? And then all the way, it minus 100 tons less than the previous day until 15 June. So this carries on. So for the n plus 2 day, I would have 1000 plus n minus 1 or 100 minus 2 or 100, right? And then this carries on all the way until 15, the 15th day. And by the time we hit the 15th day, what will be the value over here? Now, if you realize the pattern, this itself forms its own AP, and this itself forms its own AP, right? Because from here to here, I plus 100, and then from here to here, I plus 100, plus 100, plus 100 until n. But then from here, I start to minus 100, right? Minus 100, minus 100, and so on and so forth. So I can let this be my so-called T1 of the new AP, right? And this over here to be the last term of my so-called AP, right? The first AP, this is the second AP. And you realize that I minus 1 copy of 100 for the first day. And for the second day, I minus 2 copies of 100. So how can we express this in terms of this? So it's actually pretty simple. Right now, we will have 1000 plus n minus 1 or 100. But now is how many of this? How many of 100 will I have already minus? Right, that's the question. So if, let's say I write here, day n plus 1, I minus 100. I have 1 copy of minus 100, right? Minus 100, I have 1 copy of it. Day n plus 2, I will have 2 copies, right? And then day n plus 3, I will have 3 copies. So by the 15th day, we can say that this is n plus something to give me 15, right? And therefore, this something over here can be written as 15 minus n, right? So over here, I will write minus 15 minus n or 100, right? Because if n plus something gives me 15, and you realize that this number always coincides with this, right? These two are always the same, then the something is just 15 minus n, right? And therefore, this something over here is 15 minus n, and therefore this is 15 minus n, right? So I hope I'm showing you the pattern over here. So with that said, what is the formula that we can use to derive these 21300 goods? We can take 21300 is just the sum of the first AP, the series of the first AP plus the series of the next AP, right? And for the first AP, I have n days. So therefore, I have n over 2 days. The first term is 1000, and then the last term over here is 1000 plus n minus 1 of 100. Adding on to the next AP, right? So if I occupy n days already, here we'll have 15 minus n days, right? So for example here, if let's say here is 7, for example, then here we have 8 days, right? Because 15 minus 7 gives me 8. So I will just take plus 15 minus n over 2, right? This is the number of days that I have for the next AP. And the first term of the next AP is actually here, right? 1000 plus n minus 1 or 100 minus 100, right? And then I'm going to add the last term of this AP, which is this. So I have 1000 plus n minus 1 of 100 minus 15 minus n of 100. And right here, you see that we have just constructed a ridiculously huge equation. But this very huge equation gives us the value of n that we can use to derive the day in which he get attacked, right? Or yeah, the day that he essentially switched his strategy. So I'm not going to simplify this because it's going to be very, very long. But you can actually use your GC to help you do this. I'm going to show you how. So in H2 Math, right, our strategy is that for most of the things that we can solve using GC, we'll use GC. Right, so I'm going to show you the step-by-step way to do this on my GC. So what you're going to do now, the first thing, is that you're going to go to your y equals graph, okay? And then you're going to key this whole equation, key this whole thing into your GC, key GC, right? Just this whole thing without the 21300. So key this whole thing in your GC, and you're going to key this without making any mistakes. So x over 2, 1000 plus 1000 times x minus 1 times my 1000 plus 1000 plus okay, it's going to be quite some time, but x minus 1 of 100 plus alpha f1 15 minus x over 2 bracket 1000 plus x minus 1 of 100 minus 100 plus 1000 plus x minus 1 of 100 minus 15 minus x of 100. Close, close. After you key this whole equation in your GC, what you want to do is that you want to press your second table, right? And when you key your second table, you will get a full list of values over here. Now, I want you to scroll down the values of x, right? And when you scroll down the values of x, you realize that in your GC, so from GC, right, when my n value, okay, so we will contextualize it as n, even though in my GC is x, right? From n, when n is, for example, when n is 8, right, my value is 19900. When n is 9, my value is 21300. And when n is 10, my value is 22500. So it's very clear to see that n is actually 9, right? N is 9. So from GC, n is 9. And that's the final answer. I mean, that's not really the final answer, but that is the answer to the first part, right? When did he deliver the most goods to the camp? Is actually on the 9th day, right? So n equals to 9, and this is the day that he delivered the most goods, because you see the values increase until the 9th day, then it starts to decrease. So therefore, we know that the 9th day is when he delivered the most goods. And this is really the beauty of having your GC, right? Even though you have such a long equation, you don't really need to solve it by hand. You can just use your GC to help you to derive the answer. Now, how many tons of goods did he deliver on this particular day? Then this is going to be a very simple step of just subbing n equals to 9 back into my general term, right? So when n equals to 9, my goods delivered would just be 1000 plus 9 minus 1 or 100, right? And end up with 1800 tons. And that's the final answer to this question over here. Alright, so with that said, we have come to the end of the first lecture on my YouTube channel, where I go through with you the basics of sequence and series, what's a sequence, what's a series, as well as the first type of sequence that you need to know, which is your arithmetic progression, AP. In the next lecture, part 2, we're going through the portion on your GP, and in the third portion, that's where we'll go through sigma notation as well as recurrence relations. So this whole entire chapter is being broken up into 4 different lectures so that it's more bite-sized for you to understand. And with that said, I hope that this video is helpful. You enjoyed this lecture, make sure to subscribe if you're new here, and also let me know in the comment section below what you actually appreciated about this video and what you actually learned from it. All the information, all of the resources that you need is in the link in the description. And with that said, thanks for watching. If you need math tuition, WhatsApp the number on the screen over here to get tutored by me personally or the team at AO Math Academy. We have a team of teachers who will help you understand math intuitively like this. And with that said, I'll see you in the next lecture.